All right, guys, today we're going to do the first video on nuclear chemistry. There's three that go with this PowerPoint. The PowerPoint obviously can be kind of long, so, take breaks as you go and that kind of thing, right? So if you have questions, let me know. But let me get my pen running here. And, yep, all right, here we go. Nuclear chemistry. All right, so a little bit of history. Henry Becquerel Henri Becquerel, is credited with discovering natural radioactivity in the late 1800s. But some more well-known figures that are associated with radioactivity include Marie Curie and her husband. Now, she discovered radium and polonium as part of her research, although at the time people didn't know exactly the dangers of radiation. So Marie used to keep a vial of, I believe it was radium, next to her bed. It was like a little ampule, and just because it glowed. And it's not until much later that people understood the health effects or the health risks, I guess, associated with radiation. Her husband Pierre, he actually took a vial and taped it to his skin and was monitoring how it seemed to cause a burn without ever hurting. So, these people were doing some cutting-edge research, but their safety guidelines may not have been the greatest. Now, Marie did die from leukemia, which is believed to have been caused by her exposure to radiation. But Pierre, unfortunately, was hit while crossing the street, so a little bit more ignominious of death. Another individual that we've talked a bit about that definitely comes up when talking about radiation is Ernest Rutherford. He is responsible for the discovery of alpha, beta, and gamma radiation, which we're going to talk about today. So, very important. You've probably seen this picture before as part of the gold foil experiment. He actually used these alpha particles, which is 4,2 helium. A helium-4 nucleus, right, that just got shot into the gold foil. So we've seen that before, and he separated them using a magnet. So let's talk about a little bit of new vocab and some considerations about the periodic table. Number one, you might see the word nuclide. Nuclide's another term like isotope, which just talks about a different form of an element. The smaller nuclides, those underneath 20, have equal number of protons and neutrons in their nucleus. So you'll notice that helium has 2 protons, and the most common isotope has 2 neutrons. Carbon, 12, right? 6 protons, 6 neutrons. However, as the number increases, right, the number of protons in the nucleus increases, then the number of neutrons that are required to keep the element stable actually becomes greater than a 1-to-1 ratio. We can see that right here on this graph. So the ratio of neutrons to protons determines whether or not an element is stable. You can see here right about 20, where actually, let me switch colors real quick. Just a second. Why are we not working here? No, undo that. Go back. There we go. All right, let's use this color. All right, sorry about that. Anyway, there is our pen. I don't know why it looks like a mouse, but right here about, oh my goodness. Sorry about this. Hold on. There we go. Okay. Right about atomic number 20. All right, we can see if we read it across, that this straight line that is a 1-to-1 neutron to proton ratio, right, this thing right here, deviates from actually what we find in nature. So this belt, it's called the belt of stability. Any element that falls within that belt is likely to be stable, but these elements that are outside or very close to the edge of the belt, all right, they are not stable, right? They are radioactive. And so anything that's outside that belt of stability, we can look at the ratio of protons to neutrons, and we can start to see a trend, okay? So the big thing that we want to know, once you get above 20, all right, the 1-to-1 ratio goes away. Now, what is radioactivity? We've mentioned it, right? I've said, hey, these things outside the belt of stability are radioactive. But what is that? What does that mean? So radioactivity is transformative, all right? It's a transmutation reaction. It changes what the nuclei is comprised of. And if you start changing what a nucleus is made of, you'll start to change the identity of an element. And when you're changing a nucleus, you actually end up releasing a tremendous amount of energy. And there's two basic nuclear reactions that we're going to talk about. The first one is fission. And fission is when you split a heavier nuclei into a lighter nuclei. Right? So one nucleus splits into two lighter nuclei. This is what we use to make atomic bombs. I just noticed that there's a big old typo. Wow, bomb, B-O-M-B, not bond. And this is also what we use to run a nuclear reactor. The other kind of reaction is called nuclear fission. And nuclear fission actually takes lighter nuclei like hydrogen and mashes them together to make helium, or helium and hydrogen to make lithium, or so on and so forth. This is what happens in a star. All right, it creates new elements, or the heavier elements from lighter elements, all the way up through iron. If you want to make something greater than iron in a star, which obviously stars do, because here we are with things heavier than iron, you have to find a supernova. So a supernova creates enough heat and pressure to force those heavier elements together. But that would be fusion. Now, when we look at a nuclei, all right, who's going to be radioactive, it has a couple different ways it could break down. It could give off an alpha particle, which we see right here, all right, the alpha particle. It could give off a gamma particle, right? And it could give off a beta particle, an electron, all right? And those are really the only ones we're going to look at in this class, but you could also give off a proton or a neutron. You can give off a positron. You can give off a neutrino. You can give out all kinds of stuff. But the big three that we're going to look at is alpha, beta, and gamma radiation. So let's talk about those. First, alpha is symbolized by one of two things. This would be the nuclear notation for alpha radiation, and then we have the Greek letter alpha for the abbreviation. If you see either of those, what you're talking about is a helium nucleus, all right? It's positively charged. There are no electrons associated with it. It's kind of heavy, all right? It's about 4 AMU. It has a +2 charge because there are 2 protons, no electrons. And it has very low penetrative capability. So if you had an alpha gun and you pointed at me and you were like, hey, give me all your money, I would laugh at you and walk away because you're not going to get an alpha particle through my t-shirt. Now, a beta particle is an electron, and this would be the nuclear notation that we use for an electron. 0 because there are no protons or neutrons, and then -1 is the atomic number for an electron. Its identity is an electron. It's exceedingly light because it is an electron, has a -1 charge. And if you had a beta gun, I would probably still not be super worried about you trying to take my wallet. If you had a gamma ray, all right, because gammas are rays, they're energy, we show that with the symbol gamma, that's gamma right there. And then the nuclear notation is 0/0. There are no protons, neutrons, or electrons associated with this energy form. It is high energy radiation. It has no mass. It has no charge. But if you had a gamma ray gun, I'd be kind of worried. I'd probably give you my wallet. Now, for protons, because we can emit protons, we would do 1/1p for the nuclear notation. But a more likely scenario would be to use the hydrogen symbol, because a hydrogen atom without an electron is just a proton. It is the nucleus of a hydrogen atom. It weighs exactly what a proton weighs. It has a +1 charge because protons are positive, and it's got a similar penetrative capability as a beta particle. We also have neutrons, which would be 1/0n. They are slightly heavier than protons. They have no charge, and they are extremely capable of penetrating things. You have some going through you right now, and you probably don't even notice. So just to give you an example of how these things can be transmitted, an alpha particle, piece of paper, probably stop it. A beta particle, something like a door, the roof, the wall. That's going to stop a beta particle. Concrete block would stop gamma rays, and a neutron or a neutrino can go directly through just about anything. So neutrinos are actually one of the hardest particles in order to catch. Not quite the same as a neutron, but a neutrino is can literally pass through the entire Earth, which is just crazy. So let's look at alpha particle decay. How do we write this? What kind of problems are we going to see? How do we go about expressing alpha particle decay? So here's our problem. Radium-226 transmutates by alpha decay. Write the nuclear equation that represents this process. Well, it's a nuclear equation, so I want to use nuclear notation. So that's going to be the symbol A over Z, right? So this is my answer. This is what we're going to look at. So let's break this down. We have radium-226. All right, I have the symbol for radium. Yep. I have the mass number, 226. Yep. And I got this off of the periodic table. It is the atomic number. It's going to break down by alpha decay. So the alpha symbol is not in nuclear notation. So that's not good. How did I come up with this? Well, here's the deal. An alpha particle is a helium nuclide. Now check this out. We're going to divide this thing roughly in half. 226 equals 222 plus 4, if I read it across the top. Yep, that's true. 88 equals 86 plus 2. Yep, that's true. So I need the atomic number at the bottom and the mass number at the top to be true when I read that statement. So 4 plus 222 equals 226. And 2 plus 86 equals 88. And I'm conserving my matter, all right? I'm conserving my particles, all right, as I write this out. And that's it. That's our alpha particle decay. Let's look at beta decay. So we want to write the nuclear equation for beta decay of boron-12. So here we are again, all right? We've got this beta particle, but we don't want the beta. We want the nuclear notation for beta. So that's 0 over -1e. And again, I want to make sure this adds up. So 0 plus 12 equals 12. Yep, that works. -1 plus 6 equals 5. Yep, that works. So when I'm writing this out, right, let's say we're going to start with this. 12 boron 5 decay, so it's going to break down into 0, -1e, and something else. All right, so I say, what plus 0 is 12? Well, that's pretty easy, 12. What plus a -1 is 5? That would be 6. And then I look on the periodic table, right, because I know that's an atomic number. Periodic table tells me number 6 is carbon, and that's how I write my equation. Let's look at gamma radiation. All right, write the nuclear equation representing gamma radiation given off by the unstable radionuclide, wow, cobalt-60. So there it is with the gamma ray. You'll notice nothing changed. Well, why didn't anything change? Well, because if I rewrite this, right, I know that cobalt-60 is going to decay by gamma radiation. Well, I have a 0 on top and a 0 on bottom, so nothing changed. And there we are. So that's just a brief set of notes on how to write these nuclear equations. Okay, they're pretty simple. If you have any questions, let me know. And look for the next video talking about nuclear fission and fusion.